So I know we're talking about a light subject here, redesigning PKI, and as I've been talking to people about this week, there's a certain look I get when I tell them what I'm talking about, right? Because we've been doing this thing for, what, decades, using PKI, and I apparently don't take on small projects. So this is 2 years of research that I've been working on. So a little background about me. I'm one of those people that believes that if you want to solve a problem, you have to live the problem. I have run security teams for IoT devices, not just talked about IoT devices. So I previously ran security for Linksys and Belkin and Wink. I've launched 40 IoT devices from development concept to production release. And that's over 25 million actual devices in the wild, roughly, something like that. So you can blame me. I started my own consulting company called Break Security, and then over the last 2 years, I've actually worked, this will be 4 companies doing the same project. We just keep on getting acquired because apparently people care about PKI. So it's been an interesting journey. So I'm going to go through a couple things today, right? I'm going to talk about what really started this project, right? Many of these things should sound familiar if you've ever worked in security, and for those of you that don't, you're probably in marketing or, PR. So talk about what happened, right? What are the problems with IoT? What are the kind of things we've seen? And what was the impetus for creating this framework? How this framework works. And then we've got a demo, and I'll say right now the demo is not live because it takes 5 systems to run the demo, and I didn't think I'd be able to get all these running at the same time, so I recorded it. So I'll just warn you now, and I didn't want to tempt the demo gods. So what are we talking about here? TDI. TDI stands for Trusted Device Identity. It was first called OneID. When I created it, and as I said, we were acquired by Neustar in August. And the idea of the framework is to really make the communication between IoT devices to give everything its own identity. Because if you think about the way that identity works, PKI as a whole was, pinning to servers, right? Identifying things. But when you think of an IoT device, we're talking about lightweight, low-power devices that are asked to do things that your computer may not be able to do, or may be able to do easily, right? But the IoT device can't. And we're connecting things that were never connected before. So what happened? What didn't happen? So these headlines might look familiar, some of these, right? Philips Hue. Right, the hub gets hacked and people are sending things through their devices. Devices are having them being controlled by other devices within the network. Smart TVs are being hacked or recording information. Fridges are sending out malware and spam. And, well, it happens on a daily basis, right? If you look at any Black Hat or DEF CON for the last 5 years, you've seen IoT hacks. So being on the defense side, this gets kind of frustrating, right? Patching, trying to make sure. It's not a different paradigm, right? These are IoT devices. The Linux issues are no different than they were for Linux administrators 10 years ago. The difference is the experience of the teams building them in a lot of cases, right? And you're building, very similar to kind of Android, you're building the entire stack. You're not just building the firmware. You're not just building the application. And then we talk about CAs. And there's an inherent problem with the CA. The problem with the CA is someone can get root, right? Patriot Act says, hey, I want access, right? Banks have to provide access for their CAs. So you've seen Google have their intermediaries compromised. You've seen Komodo get completely owned, right? And so if you think about how that works, right? How does revocation work? Well, normally these devices are told to do a lookup, and you're asking a low-power device to do a lookup. It's not really efficient for IoT. And then there's the personal stuff for me, because as I said, I ran IoT devices for a long time. And like anyone else, I make mistakes. So I had 500,000 devices that were sitting on the internet at a time, and our private key was compromised. And that's really fun. And so when you're sitting there and you're knocking your SOC can't fix the problem because they're waiting for users to update firmware, you start to understand why it needs to change and why the model that we have right now does not work, right? So as I thought about this, it took us 6 months to fix these problems because we had to wait for all our users to update. And in fact, the last roughly decent amount of users, I actually sent them brand new devices because I was just tired of waiting, right? Just eat the cost of the product at that point. But this is what really we're talking about. It doesn't work for the paradigm of IoT. So 140 threat models, and I'm not kidding about this. For those, when I say I have to live the problem to understand how to fix the problem, show of hands, how many people have an IoT device in their house? How many people have 10 IoT devices in your house? What about 50? Anyone have 100? I have 130 IoT devices in my house. Every single light bulb, door lock, window sensor, camera, my pool is connected. Appliances are connected. My receiver is connected. My TVs, my kids have iPads, iPhones. There's 130 devices sending traffic at every single minute in my house. And you'd be amazed by the traffic that I see on that. But what I learn is what's not working with IoT, what needs to be changed. So I sat down and I drew out threat models. This all started on my living room floor with a ream of paper. And I drew out a threat model for every single device that I had ever attacked, defended, heard, saw an article about, and started thinking about what needs to change in order to make sure that the knock and the SOC, that your security teams are in control, rather than letting users or site managers be the ones. So we all know crypto's hard, right? Sometimes you need a PhD to understand it, but the whole point is for development teams, it should be easy, right? Users shouldn't have to think about crypto ever. And everyone makes mistakes, right? It's very hard to implement. There's lots of libraries. You have to make sure those libraries are even taken care of, right? Some of those libraries that are used aren't even supported very well, right? They're part-time developers who have full-time jobs doing other things. So we get it. PKI sucks. What do we need to do? So what if we change the way we think about how we need to interact with devices? What if we said, assume that everything is compromised already? The user, the service, the server, the network, the devices, it's all compromised. Start with that model and work from there so that even if the whole thing is compromised, I can still communicate. That's the basis of what TDI was. I wanted to make sure that no matter what kind of attack happened, we could recover. Now let's not mistake this. This is no silver bullet. I'm not stopping every attack possible. There is nothing that is hack-proof, right? Don't let a market team fool you. But this isn't about stopping every attack. It's about limiting the risk, but it's also about making sure that you can recover. Because if you think about what happens when you have to replace keys, that part is the difficult part. Revocation, you've got to pull that device, that public key off of every single device and server that can communicate, right? 50 devices is fine. 100 devices is fine. You start getting to 1,000 servers, 2,000 servers, that becomes really difficult, right? Time consuming. Show of hands, who has ever dealt with an expired cert? Like I said, the rest of you are probably marketing or newbies or it happens way too often. And I'll say from a personal level, it happened to me. I ran a company, an IoT device at Wink. I'd been there 3 months, and I was told it was a 10-year cert, and I made the mistake of not checking it. It was a 1-year cert. So 3 months after I got there, I got a call early in the morning on a Saturday as I was hanging out with my kids, and they said, hey, guess what? All the devices on the East Coast just disconnected. And you have 3 hours to fix the majority of our devices. That's never a call you want to get. That's never something you want to hear. That can you hack into your own device to try and fix it? Needless to say, I used NTP and DNS hack to set time back and give me some extra time. But the idea is use the flaws you have, right? I mean, work with what you've got. So what you really think about is, how do I stop this from ever happening? Because everyone's got an expiration story. And that's the sad part. It happened last week to a vendor. I won't name the vendor, but it doesn't surprise me. So trust nothing until proven otherwise, right? I don't want to trust any device on my network. Just because it's there doesn't mean it has access. I have 130 devices. There's very few of those devices I want to communicate with each other, right? My fridge does not need to know anything about my door. My receiver really does not need to know every device that's running on my network, right? It just doesn't. It wants to. It sends an SSDP request every 30 seconds, right? It's trying to do discovery of everything on my network, but it really doesn't need anything other than the DLNA stuff, right? So revocation should be instant. I should not have to sit there and wait for a user or a site manager to update the device. Think about it that way. Is a security team in control, or are your users in control of the security? We keep on talking about making security, teaching users security, but that's not the right answer. The right answer is making security work for users. So let's talk about the key terms of trusted device identity. We have what's called a fleet. So think of a fleet as a giant rubber band. Fleet is just a set of SKUs or anything that you want to identify separately. It could be a car, it could be a particular camera model. So the fleet gives us a identity. And a fleet server is just any server that is able to sign on behalf of that, right? It can be a firmware server, it can be any sort of connection server, it could be content, right? Telemetrics, whatever it is. And then we have the co-signing service, and this is sort of the heart of what trusted device identity is. The co-signing service is what validates this stuff in real time. And I'll get into that a little more. And then we have our devices, right? Anything that you're connecting. Anything from a light bulb to a fridge. So there's a lot of keys here. I know this can get very confusing, and I promise you I'll take you through it. The way we work this is that every single device, server, service, network, user has its own identity, right? And this way you can isolate it down. Nothing is shared in that way. So the device gets its own identity. The server gets its own identity. And then we have a fleet identity. And I'll explain how that works, but the fleet identity requires that the server is verified first and in real time. And then we have our co-signing service. And so for every fleet, we have a separate private public key pair. And that way, if one is compromised, the others are not. Now, the interesting thing about how you get that identity for the device, we've actually partnered up with Intel. You've got TPMs, you've got TEEs, you've got secure elements. Some of these things already have pre-provisioned identities. Great, we'll use them. We'll take the public key from that and ingest it into our framework. Your identity set. Intel's been shipping identities in their processors for 6 years. We can use that to pick it up and use that to identify. Right? So however it's done. The other part is, one of the things we're trying to achieve is, most of the time when you deal with identity, it sits in the firmware. We're tying the firmware to the hardware so that you know that the device that's communicating is in fact the device that you want, right? That it's not being spoofed. So these are the components of TDI, right? You've got our co-signing engine, which is the verification engine. We have a client app, right? Whatever mobile app you have, and then our any fleet server. So it's a small piece of code that would go on any server that you would have that would communicate with your devices. And then we have a gateway slash actual device firmware app. So what we're talking about is code signing and verification, right? Lightweight piece of code. I'm of the belief that developers' jobs should be easy when we build these kind of frameworks. So with that in mind, I didn't want a developer to ever say to us, hey, it doesn't support my language. We have C, C++, Java, Go, Python, and a couple other implementations we're working on. If you're not writing in those languages, I can't help you, but we might write another one at some other point. Let's talk about encryption for a minute. Where are my crypto geeks here? All right. So we're using the P256 curve. We wanted to be using ED25519. The interesting thing is it is not supported by as much hardware, and it requires a lot more power. So there's a trade-off of, is encryption what's being broken? And usually it's not the encryption that's being broken, so we're okay with going to a lower level encryption so we can support more devices. I talked about the size of this. Originally, it took a megabyte of NAND space. We're down to 100K and 32K of run. This is tiny, right? If you don't have room for this on your IoT device, I'd be shocked, because I've tried to make room on IoT devices that have small NANDs, small storage before, and it was never this small to deal with. So we tried to keep that in mind. And then our implementation has CLI, UI, and API implementations. So we'll talk about, there's a dashboard that you use to interface with this that you can set up in your environment. There's the code that you're going to put on your device. There's the code that you're going to put on an app, right? Again, this is signing and verification. And so however you want to interact with that, however you want to programmatically deal with that, we've got that set up. So let's talk about PKI versus TDI, right? Because again, I think PKI sucks. So PKI, I want to send a firmware update to my device. I sign it with a certificate, a key, and I send it from that down to the device. Now I ask that device to do something that a computer can do a lot easier, which is I want that device to now do a lookup to see if that server is still valid, that identity is still valid. But that's a low-powered device on a crowded network in many cases, and I'm asking that to do the workload for me, right? That's 2 round trips. TDI works very different. Before the message ever gets to the device, it has to be validated, and it has to be validated in real time. So if that server is no longer valid, it never gets a message down to the device. The other thing we do is we separated out authentication and authorization. And the reason we did this is because we wanted privacy back. Because if you think about it, does the device really need to know what server is communicating with it? Or does it just need to know that the server is authorized? And that enters the power of TDI, because you can replace the entire set of servers and the next message works fine without any update to the device. So you also have OCSP stapling, which is used fairly frequently, right? And in OCSP stapling, you have the actual verification going down with the message. The problem still lies with PKI, with IoT devices. The public keys still need to live on the device. So you're still doing firmware updates to get rid of those, right? You're still updating servers every time you add or remove one, and that doesn't work. So let's take through a couple scenarios, right? We got PKI with a CRL, right? In a shared server identity. That shared server identity, if that server is compromised, every one of your servers is compromised, right? Now you have to replace your keys. You have to put that on the CRL, and then you have to do a push to the device or a update to every single device. When you have individual server keys, now every single time you add a server, you remove a server, you add a device, you remove a device, you push public keys to everything, which is a lot of overhead, right? Again, these are low-powered devices. These are not enterprise networks, right? These can be consumer networks or SMB networks. They don't have necessarily the bandwidth for all that overhead. And then you have OCSP, right? It solves some of the problem. It sends the verification down. But guess what? You still have the public key in the device. So any breach of those keys requires everything to be removed. So let's talk about how TDI handles these, right? Any server, any device, any service, any app can be instantly revoked. And we're talking less than 5 seconds. It's as fast as you can find in the list. PKI, you have to do an update to every device, every server. With TDI, you only need to validate 2 things. The only thing that the device cares about are 2 identities. the TDI co-signing service, and the fleet. Doesn't care about the server, doesn't care about anything else. And that way, it's very powerful, and you can spin up entire new environments without having any update to the device again. So PKI doesn't work like that, right? Device has to have a key for everything it can talk to. And again, this means think of Sony, think of environments where all their servers have been compromised. Think of CryptoLocker, right? Someone's locked you out of all your servers. Well, we've thought of this because, as I said before, this was designed on everything will be compromised, so start with they all are, and how do I recover from that? So let's talk about the workflow. So if you want to create what we call a fleet, you essentially generate the identity for that. Now this can be done, if you have an HSM, you basically already have a private public key pair in there, and then you just pull the public key and upload it into the TDI service. Otherwise, you can essentially just generate that using a SDK. So now you have a fleet, and you create a user that creates your fleet administrator. Now we're talking your NOC SOC person, not an end user. So now we want to provision servers, right? These are the things that can talk on behalf of the fleet. So they're generated a key pair. The private public keys go to that server. The public key goes to the TDI service. And remember I said we separate out authentication and authorization. The only thing that stores the public key is the TDI service. And that's why the device doesn't need that update every time you add or remove. Provisioning devices is the same thing. You generate it either on device, you can pull it from the device if it already exists, and then you push the public key to the TDI service. So this service is maintaining a list of everything that's allowed to communicate, which is how we're able to revoke in real time. So this is the main workflow. This is really the heart of it. When I started this is the only thing I drew. So let's take this step by step. In step one, you've got a server that signs with its identity it's been provided. And it says, I'm trying to send a message to a device. TDI looks at that server and says, are you still valid for the fleet? If you're not, I'm going to kill that request on the vine. And the reason is we don't want an Apple fail condition. And if you don't remember that, it was certificates that were invalid, but the logic actually allowed it to go through anyway. I don't ever want that to happen, right? I don't want to trust that something has been implemented in only one place properly. So I just kill it there. If it is valid, I sign that message with the fleet key. We used to call it the project, now it's called the fleet. And now you have two signatures. The server's private key has signed the message, and the fleet has, and the TDI service has signed the message. It gets sent back to the server. The server can now grab another signature, which is the fleet signature. You now have three private keys signing a message. It goes down to the device. And again, the device only looks at two things: the public key for TDI and the public key for the fleet. It's only two things it cares about. So if I need to remove all my servers again, I remove them all. It has no idea who the server is. It doesn't care. It just knows that the server is authorized. Let's take another scenario where that becomes important. You start thinking about smart cars. And I have a smart car that's slowing down in front of me. I want my car to know that it should slow down, but I don't need to know anything about who's driving that smart car. I just need to know that that smart car is authorized to talk to me. In the way we used to do things, you used to tie identity to authorization. And the way we've separated now is I can say I'm authorized, but I don't have to identify myself to you. Device to server works a little different. It's fairly the reverse, but we do a pass-through through the server. And the reason is we don't want to have multiple paths for that device to communicate. So we don't want it communicating directly with our co-signing service. So if a device wants to go through and sign a message, it signs with its identity. It sends that through to the server, and the server passes it through to the TDI co-signing service, and that co-signing service validates it or kills it. If it validates it, it sends it back. So how does this work when you add an application? Well, as I said, everything gets its own identity. So in the application model, you generate a request from a device, it goes to the application signs with its information as well, passes it through, and it keeps on going until it goes back to the application so it can be validated. So everything that's involved in this chain signs with its own identity. That way you know if it was a valid app or if someone was trying to spoof it. That way you know if it went through a valid server or if someone was trying to spoof it. Now when you're sending it through to a device, right, again, the cosigner, the application, they're all signing with their messages, right, with their identities. I'll reiterate the thing I said before. We started with a model, or I started with a model of everything will be compromised. And when I mean everything, I mean everything. So let's say you've actually lost access to all your servers. You've lost access to your network. You've lost access to your devices. When we generate a fleet, we generate one other thing. So I'll talk about that's like I'm a slide ahead of myself, but breach recovery is really, really easy. So we have a dashboard. It lists all the servers and devices that have access to a fleet. So all you need to do is go in there. You click on the server or device you want to remove. You hit two things, either archive or pause. You can pause something and do investigation, so your NOC or SOC can determine whether it's still, whether it's a real problem. Or you can archive it. And I'm going to show this in the demo because this is the powerful part. I don't need to stop an attack on a server if I've lost access to it. I just need to revoke its access to communicate on behalf of the fleet. So even if you've completely lost control of that server, you can stop the attack. The nuclear option. Everything is compromised. When we generate a fleet, we generate 3 private keys. They're stored on a USB drive, on separate USB drives. Hopefully you store them offline. Oh. So the idea here is you've lost access to everything. You generate a request with these 3 private keys, and you include 2 new public keys in it, the new TDI public key and the new fleet public key. You can recover all your devices even when you've lost access to the network, the servers, your entire setup. And the reason is because when it gets that request with those 3 private keys, it replaces the 2 public keys it has to point to TDI and to your fleet. Let's say you're Sony. You've lost access to your environment. You stand up a brand new environment in a brand new location. You generate that request. You send it down to the device. The devices now point to the new environment. You're back up and running. Take this from a personal note. When this happens with PKI, this happened to us at Wink. We had to box up every device that was on Amazon, Best Buy, Lowe's, and in customers' homes, send it to a warehouse, put the whole team in that warehouse, and firmware flash update all these devices. It was not a fun time. We had a lot of devices. It took weeks of work, not to mention customers were not exactly thrilled. So this should never happen again, right? We need to challenge the way that things work and redesign them to make them work for the way we need to do things. If that wasn't enough, I decided to add a couple additional things, right? So we talked about the real-time provisioning, right? Everything has flexible management. Everything has its own identity. Literally everything has its own identity. It's bi-directional. We're not talking about certificate pinning here, right? It's not just the device saying, I know who the server is. The devices and servers are authenticated, right? Everything, the device tells the servers who it is, right? Tells the fleet tells the devices, the apps tell the devices, other devices tell each other that they're authorized. So it goes both ways. The other part is it's automated, right? We can roll out, I talked about 3 problems, right? Revocation, expiration, and rotation. So if I need to replace keys on a server, it's a very fast effort. It is not a 5-day effort with your NOC, SOC basically sitting there making sure they test, right? Every time I hear about teams talking about how they rotate keys, it's this giant effort, late nights, right? Long testing. That shouldn't be, you've got other stuff to worry about, right? Let's make this fast. This is now what I like to call the gravy, because I started thinking about this as, how do I attack these devices? How would I mitigate as much as possible, stop these attacks? So we call this route validation, and it works like this. You have a device on a particular LAN segment. That device signs with its identity. Now, as a researcher, it's fairly easy to clone a single device, right? Put it in Burp Suite, start sending requests out. But the question is, can you get on the right LAN segment? I can get on the right LAN, I can drop a box, but there's devices all over the network. With route validation, we put the same code that we put on the device on every gateway that you control in your environment. So when the device signs with its identity, it passes through the gateway validates anything that's supposed to be on that LAN that's allowed to communicate. The gateway now signs with its identity on top of that message. The next LAN segment signs with its identity. The next LAN segment signs with its identity. Of course, at that point, it probably goes out to the internet and then to your servers. But now you have a chain of identity, right? The device plus 3 gateways. Maybe it's 5 gateways, maybe it's 2. Our server then validates that, and when I say our server, we're talking about the fleet server that runs in whatever your environment is. Validates not only that all the signatures are valid, but it validates the order of them and the distance between them. Think about that for a minute. If someone hijacks somewhere in the middle and is looking at or trying to modify that, you see that. How does this apply in the real world? Well, think of a police officer, right? They've got a phone on them. They're recording information. They're digitally signing that information with their phone. Now they want to put that into evidence. Now that evidence storage is signing with its information. You go into court and you say, how do I know that this hasn't been tampered with? Well, it's got digital signatures and timestamps for everything. This can be applied to any sort of transaction, banking, all kinds of things, right? You know the chain of custody of this information. And if that wasn't enough, there's other stuff we're working on. And this is, I should say, part of this, we've been working with a number of partners to open source this. Dell has a project with the Linux Foundation for an IoT framework. And this code will be contributed as part of that under the Apache 2.0 license. So when I got acquired by Neustar, the first thing I thought of is, oh, Neustar's got DDoS protection services and DNS protection services. There's some pretty cool things I can do with IoT. I can use that information coming from the devices, and if I see a bunch of devices that all of a sudden are going to a certain location or a certain URL, I can take that in and then push that as an update to my other IoT devices to block that URL. Now think about Mirai for a minute. All of a sudden, these devices, hundreds of thousands of them, are being redirected to another place. If I digitally sign a whitelist or a blacklist on those devices, I can stop those devices from sending traffic to those sites. You use the power of these devices and the information they see to protect these devices. And I can scrub DDoS attacks where they start. So if I can stop the camera that's sending the attack from ever generating that attack by pushing an update down to it, I don't have to push traffic off to the cloud to scrub it. I can do it at the edge, or I can do it on the device itself. So that's something we're working on that we'll have an update to this framework. So we said real time, right? But you start to think there's other scenarios. A auto manufacturer came and was talking to me and said, hey, Brian, that's really cool, but what if I have the remote that's got an identity in it, and now my car is 5 stories underground, and it has no internet connectivity? Which is a valid point. How do I make sure that I can unlock my car rather than being stuck? So there's a couple different options here. When we talked about the gateway before, I said that the gateway can verify things that are on the local network. Well, most connected cars nowadays have gateways. So if you replicate what is the local devices on that gateway, I can verify without ever having to go out to the internet for offline mode. Now you can also do caching. If I want to say maybe 5 requests can go through, are allowed without going up, or I say in the next 50 minutes you can go ahead and have requests go through. It's flexible. The other thing that's flexible in when we talk about fleets is, I said a fleet would be a SKU, right? It actually can be fleets within fleets, and let me give you an example. Let's say Toyota wants to have their connected car have digital identities. Well, for those who haven't worked in the car space, there's about 100 different ECUs in a car, right? Different processors, different vendors. I can put a fleet within a fleet and say, okay, AC Delco or whoever this manufacturer is of this part, you can update your device and only your device. But now I can also block you from communicating to other things over the CAN bus that you're not supposed to talk to. I can stop you from uploading firmware to that because I'm going to verify in real time that whatever that USB device or that way you're trying to load firmware is authorized. But now I can also stop you from using the radio to talk to the brakes, because those two devices should never communicate. Right? You've got a gateway there that's pretty powerful. Let's leverage it. Now, device to device, right? Within a LAN, that works the same way. A device wants to communicate to another device, it can assert its relationship through that gateway through caching. And that's something that we're working on there, rather than going through the TDI co-signing service. That would lower the latency even further. Because if you think about the latency, a CRL lookup from a low-power device is a much, much slower request than a TDI co-signing service that's sitting in the cloud, which can be deployed, right, because it's open source, can be deployed wherever your servers are, as long as you separate that with different credentials, please. And so that's a very fast request. You're making it a lot easier for the devices, a lot faster. So let's take a look at what this looks like. In order to make this work, we had to build a demo. So we took the framework and we built an application, and we built some servers. And who doesn't love Legos, right? So let me frame this for you before I kick this off playing. So in the top left corner, we've got a Lego parking lot. There are 3 IoT sensors that are in the parking lot spots, and we're using actually dental floss to pull the car. Sorry, we didn't have the time to make the car move itself. And so when those cars are removed from the spots or added to the spots, it changes the sensor and sends a message to the mobile app you see on the bottom left, which tells us what spots are open, right? Something that can be easily used. Parking is a big deal, especially in certain cities. So we want to send that information so we know where we can park. In the top right is what we call the dashboard. This is where you control all your devices, all your servers, where you can revoke, where you can add. If you add a device, it's really simple. You literally copy the public key and you paste it up there. Same thing with a server. It's instantaneously going. In the bottom right is a tail of logs. And you're going to see another window pop up there at some point, which is an attack. So in that parking lot, we have 2 servers, which are Raspberry Pis. And there's 2 ways that I talked about this, right? I said you could have many servers that run, right? And you just revoke the one that is invalid. But I also said to you that you can revoke everything. So in this instance, Raspberry Pi number 1 is the only server running. And the Raspberry Pi number 2 is not in the pool yet. And so what you're going to see is we're going to attack this server. And you're going to start seeing that app light up like a Christmas tree, right? Red, green, flashing all over the place, because we're sending status changes to every spot. There's green messages on the right-hand side right now that you'll see that are saying these are valid messages. The minute I revoke that server, they're going to go red. The messages still are going. We're not touching the server. We never stop the attack. We remove the server's access to generate that attack. And finally, then we put another server in the pool, and you'll see them go green again. So it takes five monitors to run this. That's why we recorded this. It's a pretty quick demo, but so again, you see it green. It's pulling status constantly. We've moved that car back into the spot. Now it shows red, which means there is no spot available. And you'll see the polling constantly, right? Status message, what are the status of the 3 spots? It's green saying everything's okay. So now we're generating an attack. right? It's just a very simple attack. We're doing an injection and actually copying the identity. You notice all of a sudden the parking lots, even though the cars aren't moving, they're getting random status updates, right? Just getting flooded. And so in a second, in the top right, you're going to see me revoke that server. And again, the power here is I don't have to have access to the server anymore. I just have to have access to the console. Here I am revoking it. And in a second, you're going to see it go red as soon as I revoke it. Server's now revoked, and you notice the next message is now red. It's that fast. Real-time revocation. We're not talking about minutes, we're not talking about months, we're not talking about firmware updates. It is instantaneous. Now I let it run failing for a reason, because I want you to see the power. When I add a server back, now the next message went through, immediately was green. You can replace every single server in your environment, and it next message works perfectly. And again, this means that the NOC and the SOC are in control. As fast as you can patch whatever that vulnerability was, as fast as you can spin up a new image, new servers, you put those public keys in, that system's running. The people who know about security are now back in control. PKI doesn't work, right? We needed a new model. Maybe this is the right solution, right? Maybe this is the right framework to start building on, but we needed a way to get this done for IoT that scaled. And 1,000 public keys on an IoT device didn't make sense. The code, because everyone wants the code. I'm not on the right screen. So we have some of the code up. The rest is coming. We are doing a source code audit on it, and it was a little bit delayed. It will be there. And we have some interesting revisions that are coming. 2 days ago, we finished the Docker container. It wasn't fast enough for me to get it in the slide deck, but it is something that we'll be putting up. It allows this entire demo to run so you can see how this works and start using it to build on. So once we get the source code audit completed, we'll have that up there. There's information on the pages here. If you go to the Newstar TDI GitHub, there's the Python code already, and that's the signing code that you would need to implement this in any application. And you can go ahead and start using it. Like I said, it's very lightweight. Bitly Newstar TDI, and that gets you to a page that has more information about this framework. It talks about our project with Dell and the Linux Foundation and the Apache 2.0 code. And if you have questions, we have an email address, because this is not always an easy thing to understand. I'd be remiss if I don't thank a couple people here, because this is not something, this is 2 years of research, but there are a lot of people that helped me get to this. And so these are some of the people that really, Casey was the CEO of OneID, who brought me in when I had this idea and said, hey, check this out. You want to build this? Come build this. Steve, the founder, has made a number of startups and was very supportive of the work. And I got to thank the IoT team, because they make this all work, right? I just built a bunch of threat models. They implemented a lot of the code. Questions? You can use the mics.
Well, so I'm going to cheat and ask 2 questions, but they should really be quick. One is, for your crypto, are you assuming that your IoT devices have good random number generators? And the second question is, haven't you just pushed the revocation expiry problem back to your fleet key?
No, so the reason I haven't pushed it back to the fleet key is you could replace the fleet key if you wanted to, but essentially, think about it this way. Even if they have my private key, it doesn't matter, because the minute I revoke that server, it no longer has access. So without those 2 public keys, it can't do anything. It needs both. The device verifies both, and if it doesn't have both identities, it does nothing with it. And so think about it this way. I can give that private key away. It makes no difference. right? Now, if you feel safer, use the reset option, you generate a new private public key pair. But again, I'm assuming that it will be compromised. That's the whole point. And I'm sorry, the other question you asked was? Oh, random number generator. Okay, so there's two ways we do this. We do use a random number generator in the SDK. Initially, I had an appliance that uses light that bounces and was going to use that as a random number generator. But then I realized in talking with a lot of the vendors, things like NXP and those vendors are generating identities that are already in their secure elements. So it really depends on the environment, right? Some may already have identities, and I'd rather pick up that identity if you've got it in a secure element than put that in firmware. So yes, we want a true random number generator. Whether you're going to use, someone was using their lava lamps and a video camera to generate numbers. I mean, whatever that method is, right? You can either generate themselves or use our SDK to do that. It's okay, I can repeat the question.
I just wanted to add to this. I've heard that Intel has plans of adding SGA support to IoT processors. So I think with that will come with random number generation.
So the question or the comment was about Intel adding some of their identity to the IoT processor. We actually are a partner of Intel. They have something called EPID identities. And so essentially the way that works is it's a secure way of grabbing an identity for the devices. So we basically pick up the identity that's generated and then use that to grab ownership of it. Any other questions? Cool. Yeah. Sorry, go ahead.
So I know OAuth has some facilities as well for separating an operating server from an identifying authenticating server. So how does TDI compare to OAuth, or what are the key differences?
So if you think of OAuth, if I take the token off a device, I can use that token anywhere I want, right? And that token usually lives for 6 months, maybe longer. If you think of even when they started redesigning CAs after the problems, Microsoft came up with a solution to fix that. And they came up with a 135-month expiration date. I don't know who thought that was a good idea. The whole idea there is, do you really want an identity that lives for a long time, that unless you have to remove it from the device, is still authorized? Or do you want to make sure constantly that those devices, those servers are always authorized every single time? That's really the difference between OAuth and TDI.
OAuth does have facilities for shorter-lived tokens.
Shorter, but the token still lives on the device. You still have to remove that from the device in order to remove the identity.
So the bearer token spec has, typically you'll send the token along with the message, and that token comes along with it and identifies every message. So that's one approach you can do with OAuth.
Interesting. Okay. Yeah.
I'm currently using certificate-based 8021X for thousands of Windows, Mac, and Linux devices in my enterprise. I'm wondering, do you have any plans to kind of get into that space?
So it's an interesting question. I designed this for IoT, right? But it works for other things. There's no reason you couldn't do it. Now, the browser is different, right? Because with the browser, we're dealing with, it has to be trusted by that particular browser. But there's no reason why we couldn't work in those kind of situations on desktops, on other things. There's no limitation there.
Thanks.
Cool. Thank you all very much.